This is part 1 of our video on proofs. So today we're going to be looking at how to set up a proof, and we'll be doing some proofs with exponential, logarithmic, and trigonometric functions. So we are going to start with exponential functions, and we're going to try to prove that 3 to the power of x plus 3 take away 5 times 3 to the power of x plus 1 equals 12 times 3 to the power of x. Now, I like proofs because I already know what the answer is, right? This is just like doing any type of function operation question, except they're telling me what the answer is supposed to be. So it is our job to pick one of the two sides, use our exponent laws to try to figure out how to turn it into what's on the other side. So it's kind of like a little puzzle where you already know the answer, you just have to figure out how to put the pieces together. So when I'm doing a proof, the format that we follow is to split up the left side and the right side. We usually choose one side to work on and then only use the other side if we get stuck. You can do it by making a T-chart. You might have done that in grade 11 with trigonometric proofs, but I'm going to show you a different format when we get started on this question. So first thing really I need to do is pick a side to work on that we're going to try to manipulate to try to turn into the other side. So when I'm trying to choose a side, I look for something that is complicated, right? So a lot of times I try to pick things that are easier, but that is not the case when I'm doing a proof. When I am doing a proof, I want something that has lots of operations and things that I can do. So if I take a look at the left-hand side, I notice that there are 2 terms and they are being subtracted. When I look at the right-hand side, I see that there is only 1 term. And it's going to be a little bit trickier for me to try to figure out how to turn 1 term into 2 than it is for me to turn 2 terms into 1. So I always try to pick the side that I think looks a little bit more complicated. So I'm going to start by picking the left side. So I'm going to write LS for left side equals, and then I'm going to copy the left side down. So that's 3 to the power of x plus 3 minus 5 times 3 to the power of x plus 1. I am not writing down the right side. If I wanted to, I could write right side equals, and then 12 times 3 to the power of x. We usually just pick one side to work on, and then if we get stuck, we'll go work on the other. But I am going to start by working on the left-hand side. So what I like to do before I start doing anything is just try to see if I can compare and notice anything about the 2 sides. So if I look at the left side and the right side, I notice left side has 2 terms, right side has 1. So somehow we're going to have to try to combine those 2 terms, right? I also notice they both have powers with bases of 3, but their exponents are different. So obviously something has to happen with the exponents. So in working on the left-hand side, I'm going to have to find a way to combine the 2 terms into 1, and I am likely going to have to do something with the way those powers are written because it's only 3 to the x on the other side. So I'm just going to focus on my left-hand side. First thing I would ask myself, since it is a subtraction question, is, are these like terms? Do they have the same base? Yes. Do they have the same exponents? No. So they're not like terms, I can't just subtract them. Instead, what I'm going to have to do is get a little creative and see if there is a way for me to use an exponent law to make them like terms. And I mentioned before, I noticed that the exponents here aren't the same on both sides. So that tells me that something has happened with the exponents. If I look at the exponent laws that are on the page, which are also on your green sheet, I see that there is a rule here, the very first one, that has a base with 2 exponents that are being added. And I have a base with 2 exponents that are being added. So I think that we could use this rule in reverse to turn this into a multiplication question using the 2 individual exponents. This is something that we did last week in one of our lessons. So I'm going to take 3 to the power of x plus 3 and write it as 3 to the power of x, and then times 3 to the power of 3. And then I'm going to do the same thing with the other one. We're going to subtract 5 that's not going to change. But 3 to the x plus 1, I'm going to do 3 to the power of x, and then times 3 to the power of 1. All right, from here, I notice I now have 3 to the power of x's, which is what I need on the other side, but I need to simplify some of these numbers. So 3 to the power of 3 is 27. So I have 3 to the power of x times 27. I'm going to leave the 5 and the 3 to the x, and then 3 to the 1 is just 3. Okay, I cannot multiply 27 and 3 here, right? The 3 has an exponent on it, meaning I can't actually multiply unless I deal with the power first. So you can't multiply the base of an exponential function with a coefficient. But what I can do is move the 27 in front. I think that might help us a little bit. So I have 27 times 3 to the power of x. And then here, I can't multiply the 5 and the 3 from the 3 to the x, but I can multiply the 5 and the 3, that's that number at the end there. And I get minus 15 times 3 to the power of x. Now, depending on your comfort level here, right, I now have like terms. They have the same base, they have the same exponent. So if you feel comfortable, you can say we have 27 3 to the power of x's, and we're taking away 15 3 to the power of x's, and you could just subtract those two coefficients, 27 take away 15, to get 12 3 to the power of x's. If you're not feeling that confident with dealing with those exponential functions, you could go do a little bit of variable replacement. You could let a equal 3 to the power of x, and then you would have 27a minus 15a, oops, I missed the 7, that is a 27, which is 12a. Okay, now, I don't know if you noticed, when I did this, it is now equal to what was on the right-hand side. So did I manage to turn it into what was on the other side? Absolutely, yes, we did. I like to give myself a little check mark to make myself feel good about the question. And then we finish off with, therefore, left side equals right side. So you want to take your function, split it up into the two sides, right? You can also do it by making a t-chart. That also is a proper way to format it. And then pick a side and then manipulate using your exponent laws. Now there is one more thing that you can add if you like, and that is QED. QED is Latin for quod erat demonstratum, which basically means which is what was to be proven, right? So left side equals right side, which is what we needed to prove. Do I need the QED? No. Do I need the left side equals right side? Yes. So you need to write the left side equals right side. If you want to make your proof a little fancier, you can add the QED, and if you don't care, then you can leave it off. All right, that's it for proof number 1. There is proof number 2 for you to try on your own, and then I will see you in the next section on logarithmic functions.